Okay, it is 3 o'clock, so welcome back to some socially distanced astronomy, coming to you, as always, from Cambridge University. This week, we're talking about a subject that got me interested in astronomy originally, way back when I was in primary school, and we'll come on to that in a little bit. It's a very exciting subject, all about colliding black holes. As always, this is going to be an interactive talk, so if you want to join the conversation, you can hop on to Slido. The way it works is go to slido.com and enter the code black hole. I know it's hidden by this Slido pop-up, which I don't know how to get rid of in the corner. I'm sorry, but the code is in the doobly-doo underneath the video. It's black hole, all one word. Or if you want to make life even easier for yourself, you can just scan that QR code in the top left-hand corner. And we're going to be doing a few things. As always, we're going to be asking you a couple of questions as we go along. And you are going to have the chance to ask me questions, and the end of the talk is going to be all a question and answer session where I'm going to be answering all of your black hole questions. If you stick around to the very end as well, I'm going to leave a question open at the end of the talk where you are going to have the chance to kind of submit some ideas for what you might want to hear about in the future. So if you've been following and enjoying this series, you can tell us what talks you would like in the future. Okay, on with the science. Here we go. Switch back to my presentation. When black holes collide. So this is actually going to be a bit of a talk in two halves. We're going to take a bit of a detour in the second half, and that's because we're going to have to talk about how gravity actually works. Black holes crashing together, as you might imagine, are really, really kind of extreme, violent things. And what they can do is shake the foundations of the universe itself and cause waves of gravity to spread out through the universe. And in order to understand how you get waves of gravity and how the universe can really shake, we're going to have to talk a bit about how gravity actually works. But it's a really, really exciting subject, and that's the one that, like I said, when I was back in primary school, reading about how gravity actually works is what made me really want to become an astronomer in the first place. So I hope you find it as exciting as I do. Okay, so let's recap a little bit about black holes first of all. So those of you that have been listening to these lectures so far will remember that we spoke about black holes a few weeks ago. Those of you that didn't, the black hole thing is probably linked in the sidebar, and I'll add a little pop-up later on here showing you where you can watch that video about black holes. So let's recap a little bit about black holes. So black holes are things that have such strong gravity nothing can escape, right? Not even light. Even if you go at the speed of light, that's not enough to escape the gravity of a black hole. And this is what a black hole would look like. It's not a real photograph. This is like a computer simulation of what it would look like if you were in space near a black hole. And so we can zoom in and just let's have a closer look at the anatomy of a black hole. So the ring around the edge, the black circle you see, is called the event horizon. And that's like, you can think of that as the edge of a black hole. It's like the point of no return, right? And so if you imagine flying a spaceship around near a black hole, you could happily kind of fly it around. As long as you don't cross the event horizon, you'd be absolutely fine. But it's once you cross the event horizon, that's crossing the point of no return. And at that point, you get cut off from the universe and swallowed up by the black hole, and there's no hope for you. So the event horizon is the edge of the black hole. But if we zoom into the black hole, we can see what's inside and take a look at the very center of the black hole. Because the very center of the black hole, the heart of the black hole, if you like, is a tiny little dot. And the first question that I'm going to put to you is, I want to know if you can remember what this tiny little dot in the center of a black hole is called. So have a think. You have four different options. Is the dot in the center of a black hole called the event horizon? Is it the spaghettifier? Is it the singularity? Or is it called George? And while you are thinking of that, I'm going to take a look at some of the questions that you have been submitting. I will say we're going to do our best to get to as many of your questions as we can, but we get more questions submitted than we could ever answer. So if you write a question and it never actually makes it through, I'm really sorry. Just keep trying. Maybe try again next week. We do get more questions that we can possibly respond to, which is very nice because they're all very, very good questions. Okay, just a few moments more. I'm approving a bunch of your questions while we go along. Okay, let's have a look at what you guys are saying. You guys are too smart for me. I can't fool you. A full 90% of you, 9 out of 10 of you, are saying the black hole is called the singularity. You are absolutely right. I think the spaghettifier would be quite a cool name for it, but that is not, unfortunately, the official name. Okay, so you are exactly right. Yes, the black hole, the very center of the black hole is called the singularity. And this is the heart of the black hole. This is where all the black hole's strong gravitational pull comes from. It's called the singularity because it's infinitely small. It's actually just a dot in space, which is really hard to understand, right? Because it weighs as much as a star. A black hole, you take an entire star and squish it down until it's this microscopic dot. And so it's a speck in space that weighs as much as a star. And they really are beyond our current understanding. What a black hole is really strains the laws of physics to their absolute limit. So how do you form a black hole? That's what a black hole is, fundamentally. It's this tiny, tiny speck in space that weighs as much as a star. So how do you form one of these? And the answer is that most black holes form when really, really big stars die. So this is a nice drawing of a very, very big star right near the end of its life. And when one of these really, really big stars dies, it forms a black hole. And the way it works is this is a cartoon of a big star. The outer layers of that star explode off, and that's what's called a supernova. And that's what we see in the sky when we look at exploding stars. This is a real picture now from a telescope. This isn't a drawing. This is a real picture of a star that's exploded. And that's all the outer layers of that star blowing up in a big explosion. But at the same time, the inner core of that star gets squashed down by gravity and gets smaller and smaller and smaller until it becomes a singularity. And so that's how black holes get formed. It's when really, really big stars explode and the core of the star gets squished down by gravity. So how are black holes going to collide? What we're talking about today is two black holes crashing together. How's that going to work? Because things in space are separated by really, really big distances, right? If you have one black hole over here and then another black hole 10 light years away or 100 light years away, they're separated by trillions of miles. So it's really hard to see how two black holes might collide because space is just too big. The answer is that they start off close together, and they start off by being formed by what are called binary stars, and that's when you have two twin stars that are born together and are in a system together orbiting around each other, like in this picture. And it's not actually as rare or as strange as we think. We think of single stars being normal stars, right? Because our sun is a single star. But a lot of stars in the universe, maybe even most stars in the universe, are members of binary stars. That's where you have two stars orbiting around each other. And if you have binary stars that can both turn into a black hole, then you can end up with two black holes orbiting each other, right? So if you have, this is again a cartoon, if you have two stars orbiting around each other, and if one star goes boom and turns into a black hole, and the other star then goes supernova and turns into a black hole, then what you're going to have left over is two black holes orbiting around each other, right? So instead of two stars going around each other, you have two black holes orbiting around each other. And now you can see how black holes might collide, right? So if two black holes are orbiting around each other, they can just get closer and closer and closer and eventually crash. That's what actually happened. So the first time we ever actually recorded two black holes colliding together was in 2015, and this is a nice animation of what actually happened. So there was a bigger black hole in the middle and a smaller black hole orbiting around the edge, and they just went faster and faster and faster and closer and closer and closer until zip, they merge together and create a slightly bigger black hole. So that's how two black holes crash together. You start off orbiting around each other and they just get closer and closer and closer and closer until they finally crash. So how did we detect this? I said this is the one that we detected in 2015, right? We found evidence of these two black holes crashing together. How did that actually work? Because we can't see black holes, right? They're black, they're very hard to see. So how did we get evidence for these two black holes crashing together? The answer is, it's a bit like when you pick up evidence for an earthquake, right? So when you measure an earthquake, you set up a machine like this and you can measure the earth shaking around, and that tells you there's an earthquake going on. And we set up a pretty similar machine to this, and we detected a kind of a shaking in the universe that told us these two black holes crashed together. But what's actually shaking? That's the really big question, right? Because, we think of space as empty space, and so how can something shake around? And the answer is that it's gravity itself, and we're going to get onto this in a second. So this is why you see pictures like this. When you Google pictures for black holes crashing together, you sometimes see things like this: the two dots in the middle of these two black holes, and that like wavy blanket, that wavy sheet they're sitting on, is supposed to be like the universe waving around. It's waves of gravity waves coming off of these black holes. And so in order to make sense of this, we're going to have to ask a slightly different question. So rather than saying just how do we detect this, we're going to have to understand what gravity really is. Because once we understand what gravity really is, then we can understand how it can like wave and how black holes can kind of wobble the universe around. So let's talk about gravity and find out what gravity really is. So we all have an understanding of what gravity is, right? I mean, so we're quite lucky that we have gravity. Gravity is why that we're sitting on the floor or a chair or a sofa right now and not floating off towards the ceiling. And, if you go out into a park and jump up in the air, it's gravity that pulls you back down, right? So gravity is this force that pulls everything together. Gravity is also what keeps the moon orbiting around the Earth, right? It's the Earth's gravity pulling on the moon keeps it going in an orbit around it. And gravity also holds the solar system together. Those of you that have been watching these lectures since week one, I think I asked this question: what's the force that holds the solar system together? And it's of course the gravity of the sun, right? The sun is so massive. The sun, we can think of the force pulling on all the planets like a rope and pulling them around, and that holds the solar system together. And so we have this picture of what gravity really is, right? And we think of it as a force that pulls things together. Like, this is a cartoon of a famous scientist called Isaac Newton, who's one of the first people to really understand gravity properly. And, he imagined it as a force kind of reaching out from the Earth and pulling an apple downwards. And so we tend to think of gravity as a force that pulls things together. This isn't really right, and so that's a really old-fashioned view of what gravity is, but it's not the best modern way of understanding gravity. And I'm going to explain what's wrong with that. And in order to explain what's wrong with that, I need to think of a wheelbarrow race. So imagine there's a wheelbarrow race between these two identical people. We'll call them identical twins, right? They're exactly as strong as each other, and they are going to be pushing wheelbarrows. But unfortunately, the wheelbarrow race organizer doesn't really like the bottom guy very much, so he's filled his wheelbarrow full of really heavy things. Who's going to win this wheelbarrow race, right? If they're identical twins, they can both push exactly the same force, they both are equally as strong. Who's going to win the race? The answer is, of course, the top guy, right? Because an empty wheelbarrow is really easy to push, and a really heavy wheelbarrow is going to be much, much harder to push. If you push with the same amount of force, you can move a light thing really easily, and you can move a heavy thing with much greater difficulty, right? So the general point, which sounds really obvious, is that heavy things are a lot harder to move around than light things, right? So let's think about moving around heavy things and light things. Let's think about a feather versus a bowling ball. So feathers are really light, bowling balls are really heavy. If you drop a feather and a bowling ball, which one is going to hit the ground first? So if you drop both of these things because of and they're pulled down by gravity, which one is going to hit the ground first? And again, I'm going to ask you guys this question. I want you to have a think. Which one is going to fall faster? And I just want to see what you say. So have a think about that. And while you do, I'm going to get to moderating some more of your very, very excellent questions. It's really nice to see all these questions coming through, all about black holes. You can tell lots of you are thinking really hard about this, which is really fantastic. Just a few moments more while you guys have a think about that. Okay, I think that's roughly about time. Let's have a look. I'm quite interested to see what you're going to say about this. So 99% of you say a bowling ball is going to fall faster than the feather, and you are pretty much right, but there's a really interesting twist, which I'm going to show you in a minute. So let's go back to the presentation and have a look. So I'm going to show you two videos made by the BBC actually doing this experiment. First of all, and so this is in a really, really high tower. They've taken a bowling ball and a feather up to the top of a high tower, and they're going to drop them both at the same time. And so first of all, let's see what happens when you drop a bowling ball and a feather. It's kind of the obvious thing, right? The bowling ball falls really fast, the feathers fall really, really slow. But interestingly, and this is the really important point, that's not because the feathers are lighter, it's because of air resistance. Like bowling balls can just punch through the air really easily. Feathers kind of have to waft through the air, a bit like having to kind of weave your way through a crowd, a gig or something. The feathers have to kind of move the air out the way, and that's a lot harder. If you get rid of the air, the bowling ball and the feather will fall at exactly the same speed. Which seems kind of crazy, right? It seems hard to believe, but they've done experiments on the moon. They've taken a feather and a hammer on the moon, and they drop them both at the same speed, and they land exactly the same time. And I can show you a video of it here. So this is exactly the same experiment in exactly the same place, and they're dropping a bowling ball and a feather. But this time they've taken all of the air out of the tower, so there's no air resistance for the feather to have to fight through. And watch what happens. So they drop the bowling ball and a feather, and watch them drop. So the Earth's gravity is pulling on the bowling ball and the Earth's gravity is pulling on the feather, and they are both falling at exactly the same speed. It's kind of amazing. It's really, really bizarre to see, isn't it? But this is what actually happens. Light things and heavy things actually fall exactly the same speed, and you're going to see them hit the ground like now. You can see them hit the ground at exactly the same time, and that's because light things and heavy things fall at the same speed. You can do the experiment yourself if you have like a tennis ball and a baseball or something at home, right? A baseball is heavier than a tennis ball, so you might think it would fall faster, but if you drop a baseball and a tennis ball at exactly the same time, they will land at the same time, and that's because gravity pulls everything down at exactly the same speed. So even though bowling balls are heavier than feathers, they fall at the same speed. And so the same amount of gravity is pulling on both the bowling ball and the feather, right? You know, they're both being pulled down by the same planet. And this should make you think, well, hang on a minute, there's something a bit strange. Shouldn't the bowling ball be harder to move? Remember what we were saying about the wheelbarrow? The whole point of the wheelbarrow, the wheelbarrow race experiment was that if you use the same force, a heavy thing is much, much harder to move. But the same planet is pulling down the feathers and pulling down the bowling ball, and even though the bowling ball is much, much heavier and should be harder to move, it lands at exactly the same time as a feather. Right, if you want to move a heavy thing and a light thing in exactly the same way, like if you imagined these two people to push the wheelbarrows in the same way, the bottom guy is going to have to be pushing the wheelbarrow much, much harder. Right, you're going to have to be doing a much, much harder work to keep up with someone with an empty wheelbarrow. And so this is really strange, right? How does gravity know to pull on the bowling ball harder to make it like fall faster than the feather? It doesn't really make any sense. And you're right, it doesn't really make any sense. So I'm going to say something very quite strange now. It's going to sound bizarre, but I will explain it in a second. Gravity is not really a force. We think of gravity as a force, right? Like it's the force of gravity. It's Earth reaching out and kind of pulling on things downwards. That's how we used to think about gravity in the olden days, but it's kind of not right. Gravity is not a force. So this is very, very weird, right? And so if I'm going to tell you that gravity is not a force, I need to tell you what gravity really is. Why do things fall down if there's not a force? And so I think this is the best way I can explain it. So let's imagine that we're looking at a couple of ants out for a walk across a flat field, okay? And these ants are just walking in straight lines across the fields. And they are walking along this completely flat field until they come to a rock that's kind of bending the fields down, right? So there's the really, really heavy rock that's kind of pressing into the surface. The ant that's far away from the rock can happily walk up in straight lines, but the ant that's close to the rock is like the path is going to get kind of wonked around by that bent surface, right? Because the ant is kind of getting into that depression, that divot, that hole made by the rock. It's going to kind of affect the ant's path. And the ant might think, well, hang on a minute, that rock just pulled me towards it. And of course we know that's not true, right? The rock didn't pull the ant towards it. All that happened was that the ground was a bit bent and that affected the way the ant was walking. And the ants might even play some games, right? Because the ground is bent down like a racetrack. They could notice that when they run up to it, their path gets wonked around. And if they get the angle just right, they could kind of like swing all the way around it like a racetrack. And so if this ant was really smart, we'll say it's like a scientist ant or something, the ant might say, I've discovered a force. I've discovered that rocks pull ants towards them. Because that's what it seems like to them, right? They're walking along very, very happily, and then when a rock comes along, they kind of feel themselves getting pulled towards the rock. Of course, we know that's not true, right? Because we can actually see what's happening, and the rock isn't magically pulling on the ant. All that's happening is that the surface that the ants are walking on is bent, is kind of squished by the rock. And so this is the really important thing. Even though the ants feel like the rock is pulling them around, that's actually not happening. There's no force that the rock is pulling on the ants with. All that's happening is that the rock is kind of bending the surface that the ants walk on. And so the ants are doing their best to walk in straight lines, but their floor is actually wonky. So the reason I'm telling you this, it might sound a bit weird to start talking about ants and rocks in the middle of a talk about space, but the reason I'm telling you this is because this is how gravity actually works. Like, this is what gravity actually is. So instead of a rock like bending a floor, you have the earth bending the space around it. And instead of an ant, you have like anything that's being attracted by the earth. Like, imagine a satellite or something. A satellite that's orbiting the earth isn't going round and round because there's a force pulling on it because of Earth's gravity. It's actually because Earth bends the space around it, just like a rock in a field, or like imagine like a heavy weight on a trampoline or something, kind of bending it downwards. Earth is bending the space around it, and that's what we feel as gravity. And that's what gravity really is, right? So the best way to think about gravity, the most modern way to think about gravity, is not as a force. It is all about bendy space. Earth and everything else in the universe cause space to bend. And that is what gravity really is. So this is a way of thinking about gravity that was invented by a guy called Albert Einstein. He came up with a theory of relativity. So Einstein, maybe the most famous scientist of all time. The theory of relativity, one of the most famous scientific theories of all time. And it's all about what gravity really is. He was saying that gravity is not this kind of magic force that reaches out and pulls things. It's all about just the fabric of space being bendy. And that's true absolutely everywhere, right? It sounds a bit strange if you think about outer space being bendy, but it's even stranger if you think about space just around you being bendy. If you go out into the park and jump up in the air, the reason that you fall down to Earth is actually not because there's a force pulling you downwards. It's because the space around you is bent. Right now in your room, the space around you is bent. If you pick something up like a cushion and drop it down, the reason it falls down to Earth is because the space around us is bent by the Earth's weight. And so this is the really, really big discovery, that space is this kind of bendy thing, right? There's this fabric of space. Einstein called it space-time. You can think of it as the fabric of the universe, and the whole fabric of the universe is bendy. And this is what gets shaken about when black holes collide, right? So this is what we're detecting when we listen to the universe and we can detect black holes colliding. What is it actually gets wobbled around? What gets shaken is this bendy fabric of the universe. This is the thing that the universe is actually made of. And so this picture might start to make a bit more sense now, right? So you can see these two black holes crashing together, and these waves that look like this kind of blanket or something around the black holes. This is space-time, this bendy stuff that's what gravity actually is, and that's what gets kind of rippled around and shaken around when two black holes crash together. It's the fabric of the universe itself that's bendy, and it gets rippled up into waves when black holes crash together. And that's why we can detect black holes using a machine a bit like this. What we're detecting are these waves of gravity, these waves of the whole universe kind of rippling around as it comes over, like as this wave from two black holes crashing together comes over us. So these collisions are very, very extreme, as you can imagine. Crashing black holes together in a way that's powerful enough to make the whole universe wobble has to be a ridiculously powerful crash. And they really are. So I'm going to give you a number now, which is how much energy these black holes crashing together are going to release. And it's a number in watts. You can think of watts are how we measure energy. If you look at a light bulb, it will have a number in watts on the sides. So black holes crashing together release this much energy in watts. And that is a very, very big number indeed. It's a number that's so big it doesn't even have a name. It's like a trillion, 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 trillion watts. I don't even think there's a name for a number that big. So that is the most enormous amount of energy that you can even imagine. And so right before the end, what I want to do is talk about some other types of energy to try and get an idea about how powerful it is when two black holes crash together. So at the very low end, we have low energy things like a laptop or something uses about 20 watts, so not very much at all. And then if you want to get something a bit more powerful, you might look at a car and say a car uses about 50,000 watts when you're driving down the road, which, a lot more than a laptop, but it's still a lot less than 360 trillion, 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 which is what you get when you crash two black holes together. Planes, the energy, the power required to make a plane fly is something like 10 million watts, which again is a much bigger number. That's a number with 6 zeros, right? So a million means 6 zeros. And when you use big numbers, sometimes you just have to count the zeros to get an idea of how big they are. So planes use something like 10 million watts, which is 6 zeros. A rocket taking off, like if any of you watched the SpaceX NASA launched a few days ago, a big rocket taking off like that is going to need have a power of about 10 billion watts, which is a number with 9 zeros after it. Which is starting to get quite big, right? I mean, 10 billion watts sounds like quite a lot of energy. It's a lot less than the 48 zero number, which is when two black holes crash together. So we're still looking at something that's quite puny. What about the whole world? The electricity usage of the entire Earth is only about 15 terawatts, which is a number with 12 zeros after it. So that's how much electricity the entire Earth is using. So that's obviously a very, very big number. It's still absolutely minuscule compared to two black holes crashing together. So we're going to have to get a lot bigger than the Earth if we want to understand how much energy there is. What about the sun? The sun is by a very long way the most powerful thing in our solar system. Do we think the sun is going to be more or less powerful than two black holes crashing together? So the power of the sun gives out about this much energy, which is a number with 24 zeros after it. Again, I need to stop saying, so that's about 380 trillion watts, which is a vast number, right? Too much to even imagine, but it's still the tiny, tiny, tiny fraction compared to black holes crashing together. Remember, that's a number with 48 zeros after it. So the sun is absolutely nothing compared to two black holes crashing together. Well, if we zoom out even, let's look at our whole Milky Way. So our Milky Way is a pretty big galaxy, something like 200,000 million stars in our Milky Way, and the entire power output of our whole Milky Way is a number that's about this big. So that's a number with 36 zeros after it. So that's an unimaginably big number, right? If you thought the sun was powerful, this is much, much, much more powerful. This is still like 1 trillionth of the power of two black holes crashing together. A black hole is two black holes crashing together is like 1 trillion times more powerful than all of the stars in our galaxy added together. And in fact, like this is the kind of the final result, is that you can't compare the energy of two black holes crashing together with anything, because they release more energy than every single star in the observable universe, which to me is the most mind-blowing thing. So every single star in the entire universe that we can see added together is not as powerful as two black holes crashing together. And so that's why these explosions, these crashes are amazing to study. They are the most violent, the most energetic things in the universe. They're powerful enough to shake the foundations of the universe itself. And we have been going for half an hour, which I think is a good place to finish. Thank you for voting on the questions so far. I'm going to just approve a couple more of your questions before we go through and get some answered. Okay, where are we? So I'm just wrangling my phone up. Let's switch over. Okay, questions. Fantastic questions coming in. Henry B having 2 of the top questions. Well done, Henry B. First question. If two supermassive black holes collide, do they get a new name, like a supermassive black hole? Unfortunately, no. It would be kind of cool if they did. The reason for the answer being no is that there are actually just two types of black hole. we don't just call black holes supermassive like if they get big enough. It's really a distinct type. There are what's called stellar black holes, which are what you get when stars die, and they're like roughly as big as a star. Right, they might be 10 or 100 times the mass of a star, but they're kind of down that end of things. A supermassive black hole can be millions of times as much as a star, and as far as we can tell, there's nothing in between, right? So you're either kind of pretty like star sized, or you're millions of times the size of a star, or billions of times the size of a star. And as soon as you get into that later category, then you become a supermassive black hole, and that's it. So yeah, if you get two supermassive black holes and crash them together, you still call the end result a supermassive black hole. It's just a bigger supermassive black hole. Where are we? I need to tick that one off because I've answered it. Great question. Callum B says, how many times have we seen black holes collide? Off the top of my head, I can't actually remember. It's a handful of times. We saw the first one in 2015, and we've been finding more ever since. And we think soon we're going to find lots more because we're building more and more powerful detectors all of the time. But we haven't seen thousands of these things. We've seen like a handful of these things in total. It's not necessarily because it's quite rare. So black holes we think are probably crashing together quite a lot, but it's just we haven't yet built detectors that are quite sensitive enough to see them all. Really good question, Callum. Anonymous says, when two supermassive black holes collide, does it change the source of gravity inside the black hole? And so when two supermassive black holes collide, then yes, they will form an even bigger supermassive black hole, right? And if you have one supermassive black hole that weighs 10 million times as much as the sun, and you have another supermassive black hole that weighs 10 million times as much as the sun, you add them together and you're going to get one that weighs 20 million times as much as the sun. So two massive black holes, they do add their gravity together. So the answer is really yes. I think the important thing to remember is that even though 20 million times as much as the sun is still a very, very big number, it's still quite small compared to the galaxy itself. So the gravity of the supermassive black hole is not what holds a galaxy together, right? The galaxies are held together by the gravity of all of their stars. But absolutely, when you add two black holes together, the final black hole kind of has a gravity that is equivalent to the two that's added together. Very nice, anonymous person. Akira says, if there are stars around the two black holes, do the stars create a supernova and blow up the two black holes? I don't think it's possible to blow up a black hole, because if you think about what blowing something up really means, is kind of taking the atoms inside something and kind of like scattering it around, right? If you were to, blow up a football or something, you would put a piece of dynamite inside a football and all the bits of the football would go flying off all over the place. And, when a star goes supernova, the star blows up, all the bits of the star kind of get scattered off across space. You can't really blow up a black hole like that because black holes aren't made of atoms, right? A black hole is a singularity. It's this tiny, tiny, tiny speck in space, and there's nothing to blow up. It's a tiny dot, smaller than an atom. So there's nothing to blow up. You can't blow up a black hole. Fantastic question, Akira. Another question from Henry B. Very nice. Are black holes attracted to each other? The reasons galaxies collide. It's a really good question and it's really good thinking, but the answer is no. But it's no for an interesting reason. And that's because, it's what I said before, that as big as black holes are, they're still pretty puny compared to the galaxy as a whole. So the galaxy in the Milky Way, the galaxy in the center of our galaxy is called Sagittarius A star, and it weighs something like 4 million times as much as the sun. But the galaxy as a whole, the whole Milky Way, weighs like 200,000 million times as much as the sun. So the black hole is a tiny, 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 tiny speck compared to the whole galaxy. So galaxies collide and are attracted towards each other because of all the stars in them, not because of the black holes. But very, very good thinking though. Malachi says, how many black holes are in the universe? And the answer is a very, very big number, absolutely. So in terms of supermassive black holes, every big galaxy has a supermassive black hole. So the answer is one per galaxy. And because we know there are hundreds of thousands of millions of galaxies in the universe, that means there are hundreds of thousands of millions of supermassive black holes. But as for stellar black holes, ones that are left over when stars die, there are even more. Every galaxy will probably have millions of black holes left over from when stars die. So the answer is a very, very, very big number. Yes, lots and lots and lots and lots. Very good question, Malachi. Tristan, age 7, says, what's a white hole? This is a really interesting question. So a white hole is something that is theoretical. And what that means is that you can go to your kind of equations of physics, you go to your physics textbook, and it's possible to write down an equation for something that looks like a white hole. And what it would be the opposite of a black hole. Right, so a black hole is something where the gravity is so strong that nothing can escape and it kind of sucks in everything around it. A white hole would be the opposite. It's like a black hole in reverse. It'd be a tiny, tiny speck in space that just kind of is constantly kind of spewing out material, and there'd be no way to get near it, right? Because just like a black hole, you can't escape getting sucked in. A white hole would have kind of strong anti-gravity, and there'd be no way to get near it, and it would be constantly shooting off things into space, like the opposite of the way black holes kind of swallow things up. The problem is that we're not sure if white holes are real. I think for my bet, white holes probably don't actually exist. So just because you can kind of write down, just because they're theoretical and like a physics textbook says they might exist, we don't know any way of actually making them, right? Like black holes are really weird, but we know they can get made when big stars die, right? So you take a big star, it explodes, you make a black hole. We don't know of any kind of equivalent way of making a white hole. So as far as we know, white holes, so what they are is like the opposite of a black hole, but sadly they probably don't exist. They do make kind of cool stories in science fiction, which is why they show up in things like Star Trek, because they're kind of nice ideas, but they might not exist out in the real universe. Callum B says, when did we first see black holes collide? So the first detection was in 2015, so about 5 years ago now. We have to use the word see a bit loosely, right? Because we can't actually look and see these two black holes colliding, but we detected the gravity waves, right? So remember that two black holes crashing together, it's so powerful, so energetic, it kind of makes the whole universe, the fabric of space-time, kind of wobble and ripple around. And this, we detected that in 2015. A space person says, how big is a singularity? It can't be infinitely small or it wouldn't exist. I don't think that's true, space person. So something can be infinitely small and still exist. So there are particles in atoms, like electrons, for example. Our best model of an electron in an atom is that they are infinitely small. We call them point particles. They're literally just dots. And a black hole could be the same thing. According to all of the laws of physics, as we know at the moment, black holes are infinitely small. It doesn't mean they don't exist. It just means they're all almost like little tears or little tears in the fabric of space and time. There might be some future discovery that says that black holes are not infinitely small. They're just they're really little, but not infinitely small. But that would need more like future physics that we don't understand and that we don't know exists right now. So according to all of the laws of science as we know them right now, we think that black holes are indeed infinitely small. And it doesn't mean they don't exist. It just means they exist and they're infinitely small. Tristan, how long does it take for black holes to form? That's a really good question. So black holes pretty much form straight away. So as soon as you squash anything down small enough, it will become a black hole. So inside of a star, when a big star explodes at the end of its life, that happens in a very, very small amount of time, just like a few seconds or even less. So a black hole can form very, very, very quickly, especially if you have all of the really, really strong gravity inside a dying star. That can squish a star up in like a second or something and form a black hole. So yeah, as amazing as it is, they can form very, very, very quickly. Robbie says, do black holes make galaxies heavier? And it's an interesting question. So, in a way, the answer is yes, right? Because, black holes are things with mass that exist inside inside galaxies. Sorry, if you had a magic wand and you could magically make all of the black holes inside of a galaxy disappear, then yeah, it would get lighter, right? Because black holes are things with mass, and if you got rid of them, the galaxy would be lighter. But black holes don't get heavier when they're made, because you have to make a black hole from stuff originally, right? The life cycle of a black hole starts with a cloud of gas in space, and then the cloud of gas kind of gets squished down by gravity and forms a star, and then at the end of that star's life it explodes and leaves behind a black hole. And all of that stuff has mass, right? The black hole has mass, but the star that made the black hole has mass as well. The gas cloud that made the star has mass as well, and that was in the galaxy beforehand. So black holes being made don't make galaxies get heavier and heavier, because all the stuff that goes into black holes exists beforehand. It's just when it turns into a black hole, it's putting it into a different form, if you like. Okay, we're getting up to about 40 minutes. I'll do a handful more questions and finish. Mint, age 10, says, when does a supermassive black hole eventually die? So supermassive black holes, they will die eventually. It takes an unbelievably long time. The person that discovered that black holes eventually die was called Stephen Hawking. He was a very famous astronomer here in Cambridge. And what he worked out is that black holes can slowly leak energy out into the universe. And every time they leak a bit of energy, they get a bit less massive. And then over a really long time, they eventually get smaller and smaller, and then disappear into a poof of nothingness. The problem is, this takes such a long time, you can't even imagine it. So the universe right now is 13 billion years old, 13,000 million years old. The age of the universe is like a second compared to how long it would take for a supermassive black hole to eventually die. So they will eventually evaporate into nothingness, but it would take it would take an amount of time that makes the age of the universe just seem like nothing. Can a black hole gulp another black hole? Absolutely. This is really what we've been talking about all today. Two black holes crashing together. They merge and form a slightly bigger black hole. Like, imagine rolling out two pieces of pastry or something on the kitchen side. If you have a smaller and a bigger one, you mush them together and you just end up with a slightly bigger ball of pastry that is made when you combined the two things. And that's what it's like for a black hole. They get added together and just form a slightly bigger black hole. Tristan, what happens when two supermassive black holes collide? It's basically the same as we've been talking about as we go along. The two black holes get closer and closer and spiral together and eventually crash together. It would just release an absolutely unbelievable amount of energy, and you would end up with one even bigger supermassive black hole. So it's like everything that we've been talking about all of today, just on a much bigger scale. Okay, last couple of questions. Do stay around till the end, because there's going to be one last live poll that I'm going to leave you with, because I want your feedback on things to learn about in the future. So yes, last few questions. Vihan says, do black holes move in and around space, and can it suck up our solar system or our planets? So black holes kind of do move around space in the same way that everything moves around space, right? The sun is orbiting the center of the Milky Way galaxy as the galaxy spins round, and all of the black holes in our galaxy will be doing the same thing. I think luckily there's two things to say here. First of all, black holes are not like big cosmic vacuum cleaners that go around sucking things in. They're just things that have gravity like everything else. If you go near a black hole, as long as you don't cross the event horizon, you can be perfectly safe. And so there's nothing to say that a black hole would suck up our solar system anyway. But secondly, even the closest black hole is hundreds of light years away, or even thousands of light years. So the closest black hole is a very long way away. And even if one got close, it wouldn't be the end of the world, because they're not like big cosmic vacuum cleaners. They're just things with gravity like anything else. Okay, I'm going to make this the last question, I think, from Sebastian. Could two white dwarfs colliding emit gravitational waves? The answer is absolutely yes. And in fact, this is going to sound strange. It's a good fact to leave you with. anything emits gravitational waves. If I kind of like wave my hand backwards and forwards in front of my space, in front of my face, that's going to emit gravitational waves, right? I'm kind of wiggling my arms around right now. That's emitting gravitational waves out into the universe. It's just those gravitational waves are so unbelievably tiny. Detecting them would be impossible. We can only detect the biggest collisions of all, which is when things like black holes crash together. But absolutely, yes, neutron stars crashing together, white dwarfs crashing together, stars orbiting each other, even the Earth going around the sun, the moon going around the Earth, everything emits gravitational waves. But just so far, we can only detect the most powerful things. Thank you very much for listening. I'm going to put up this question, which is the one I'm going to leave you with. And this question is not going to it's not going to finish with the talk. I'm going to leave this open. So even when I've hung up, this is going to stay open for a few days, so you can have a think. What I want to hear about is from people that are listening to these talks, what kinds of things would you like to hear about in the future? Maybe you want to hear more about planets around other stars, or aliens, or missions to space, or any kind of thing like this. So I'm just going to leave this open for the next few days. So have a think and come back and let us know what you would like to hear about, and then we could design a talk just for you. Thank you very much for listening. If you've enjoyed this, please consider giving our channel a subscribe. That way you can stay up to date with all of the really cool, exciting astronomy things we have going on. We have these talks every Tuesday. We've got another one next week, all about the disks that form around young stars, which tells us how planets form. We have Ask an Astronomer streams every single Monday evening. So if you have astronomy questions that you didn't get to ask on these ones, come along Monday night and you can ask astronomers live. And then every Friday we put up a nice public talk for you to watch over the weekend and learn about some more astronomy. So thank you very much, everyone, for listening, and we will be back with you next week.